Hello and welcome back to the Home Lab. Looking a bit smarter today because I've been in school teaching mathematics. Anyway, I've got a really interesting build to show you today. What we're going to look at is how you can build logic gates using regular electromechanical relays. Just before we start, a big thank you to all of you again for watching my videos and taking an interest in what I do. And also to PCBWay, who sponsor me and encourage me to make more material. As you know, they do CNC machining and 3D printing, and they're particularly well known for the bespoke circuit boards they can make for you. Anyway, go and have a look at their website. There are lots of interesting ideas for projects on there as well, and I'm sure you'll get some inspiration for the next project that you want to try. Now, I'm sure you're all familiar with the way logic gates work, but if you're not completely up to speed with how AND, NOR, NOT and NAND gates work, perhaps have a quick look at my video on making logic gates out of reed relays. But what we're going to do today is take it a step further and look to see if we can make logic gates out of regular electromechanical relays. Now, I'm sure you're familiar that a relay is something that has an electromagnet in it, and when that electromagnet is energized, it pulls an armature across and pushes lots of contacts together. Again, if you're not completely up to speed with how relays work, have a look at the video I did on the operation of a relay. So, if you know something about how logic gates work, and you understand a bit more about how electromechanical relays work, we're ready to have a look at how we can build a little circuit that uses electromechanical relays to do logical functions. So I hear you say, why build a board that uses electromechanical relays to do logical functions? Well, there's a number of reasons for this. Certainly on the railways with signalling, back in the day, and maybe even still now on a lot of the lines, they use relays and all sorts of interlocks to do certain logical functions for signalling. You know, if A and B are on, then C should not be on, etc. So I thought it might be quite interesting to see what we could do with relays. Also, very early computers would have used relays as part of their logical functions because they didn't have semiconductors to do that, or at least some of the valves or tubes, as Americans call them, were very, very early in their development, or at least very, very unreliable. So they went to a system that they knew very well and could be easily hardwired together to make the logic work. So what we've got to do now is have a quick look at how I went about building this, and then we'll look at how these relays can be used to do regular logical functions. So a quick look at the build process, and you're getting pretty used to the way I build these things. So the first thing to do was to jot a few things down on bits of paper, and I went through quite a few iterations of how I was going to lay out the relays, and particularly just working out in my head how you could get logical functions from a group of relays and what was the minimum number of relays you could use. I then went to my go-to material, which is always A4 Perspex, and drew out the sort of plan that I wanted, and then there was a whole load of cutting and drilling, as there always is. And then I drew on the wiring that was needed on the board, and I also had to make lots of 4mm leads to plug everything together. It was then a case of getting the right relays, and so I bought a box of relays, and it turned out that I bought ones that only had one type of contact. I think that was a make contact, which I didn't really think through, so I then had to go and buy a few more which had both make and break contacts, which are particularly useful for doing OR gates. Anyway, put all that lot together, and I ended up with something I'm quite pleased with. So this circuit with a sort of nest of wiring behind. So what we'll do now is we'll wire it up, and we'll have a go at showing how wiring these relays can produce different logic gates. Let's have a quick tour of the board. So I've got 5 volts coming in here to power the relays from my bench power supply, and 3 individual relays and all of their terminals on these 4mm plug sockets, so they're not wired up yet. We're going to be using just one relay, this one for our first gate demonstration. Then for most of the others we're going to need 2 relays because there's going to be an A and a B input. And then finally when we do an SR latch we're going to have to use all 3 relays. So I've got pictures of the relays here, schematic of how they're laid out, and the wiring that does exist currently underneath the board. And these are LEDs that are going to indicate the states of the outputs, and here the state of the input, A and B. And finally, I've got a little truth table here so we can draw in the truth table for the gate that we're building. Right, so to get you used to what's going on here, let's kick off with a simple buffer. So you know that the truth table for a buffer is really quite simple. It's just 0 on A and the output is 0, and a 1 on A and the output is high. So good for sort of squaring up signals and repairing digital signals that have got a little bit weak. So to do this, we've got power coming into the board, and I'll very quickly wire it up. We're going to need positive coming into the relay here. We're going to use this middle relay. So we're going to make that terminal plus. That relay has got a switch that's normally down here. So I'll draw that in. There we go. And finally, I've got to do a little bit of wiring for this part here. So I've got to make one side of the coil negative, and the other side of the coil is going to be the input A. So here's my lead with A on it, so I'll plug that in there. And finally, I need this wiper, the switch part of the relay, to be positive as well. So that's here. And I won't do this for every gate, but I'm just sort of showing you how I put it together. Okay, so let's switch on and see what happens. Looking at this relay, you can see we've got 2 outputs, Q and Q bar. We're only looking at Q, the output from the buffer. So let's switch on the power supply. There we go. And you'll notice at the moment, if I take an input A and I make it low, so I'm going to connect to here, which is the sort of 0 point, the output is low, and obviously the inversion is high. And then what I'm going to do now is make the input high. I'll stick it here so you can see more clearly that I'm making it positive. And there we go. The relay switches because input A is now high and output Q is now high because the coil has been energized and the relay is flicked to the up position. Right, let's look at the inverter now. So, as I'm sure you know, the inverter is the opposite of a buffer. So when the input A is low, the output Q is high. And when the input A is high, the output Q is low. You know the symbol and the little circle there to show that it inverts its input. So the circuit is identical, but this time we're going to use the lower contact of the relay to be Q, the output, and the top one we can ignore, or you can imagine that's the inverse of the output that we get. But it's this one here we need to look at. So I'll switch on the power supply. There we go. And you'll notice when A is low, the output is high. I'll just prove that A is low, so I'll connect it to 0. And then what we'll do is connect the A input to high, and the relay switches over. A is now high and the output is now low, and of course you might remember this LED will come on because that's the inverse of the inverter. Right, time for the AND gate now. You're all familiar with the AND gate. The output Q is high if A and B are high, and all the other situations the output is low. So here's the output of the gate, and that's Q. The inverse of it there is Q bar, and we're going to make this the A input and the B input relay. So we're going to use 2 relays. I've done all the wiring already, so let's turn on the power supply. There we go. and currently A and B are low, but I think we need to prove that, so we'll connect them together and connect them to a point that is 0. So A is low and B is low. Let's now go for A is low and B is high. So there's B, and we'll make that high. So B is high, but Q is still low. Then we'll swap it around. So we'll make A high and B low. So A is high and B is low, and the output Q is low. Just ignore Q bar for a minute. It's only Q I'm really interested in. And finally, let's make A and B high. So the A and B leads, I'll connect them together, connect them to a point that's high. So there we go. A is high, B is high, and the output Q is high. So these two relays are working really well as an AND gate. Great, well, I'm sure you're really getting the hang of this now. So let's have a quick look at the NAND gate. So you know the NAND gate is the opposite of the AND gate. The output is not high when A and B are high. So A and B are high, the output is not high. And the output here is Q. And here are my two inputs. Now I've had to do a bit of wiring here. You'll notice that the positive is coming through this relay. It's currently high all the way along here to the output of this one, which is now high. So we've also got a positive wired to this switch as well. So let's see how the NAND gate behaves. So to start off with, we need 0, 0, so both are low. So if the two inputs are low, the output is high, that's right. Let's make A low, so that's A, and let's make B high. And there's lots of clicking going on here because B has gone high, but A is low, and the output is still high. Then we'll reverse them. So there we go. A is now high and B is low, so the output is still 1. And finally, what makes it a NAND gate, let's make both inputs A and B high. And if we do that, lots of switching going on with the relays. A and B are high and the output Q is now low. So two relays working as a NAND gate. So let's now quickly look at the OR gate. So the OR gate, you know that the output is high if A or B are high, and if both of them are on high, well, that's fine. That still means that A or B are high. We'll do the exclusive OR a little bit later. So I've wired up the two relays again here slightly differently. Look at the two positives coming into these switches, but now I've got a wire coming from this wiper across and to that output. So let's switch on the power supply. There we go. And we're looking at the output here, Q, and the inputs A and B. So currently A and B are both low. And as we'd expect, the output Q is low. Let's make A low. So I'll keep that plugged in there. And let's make B high. So you'll notice that B goes high and the output here is now high. Let's swap them round. There we go. So swapping them round shouldn't make any difference at all. A is now high and B is low, but the output Q is still high. And finally, the really important one is two highs. And if A and B are high, then the output is high. And that can be a bit of a problem, so we need to change this so we can turn it into an exclusive OR. But perhaps let's do the NOR gate first. Right, so now let's quickly look at the NOR gate using two relays, and you're familiar with the NOR gate, the inverse function of the OR gate. So the output is high only when A and B are not high, and all other configurations the output is low. So I've done a bit more rewiring here, and you'll see that I've fed the positive through this wiper and then into the input of the second relay, and this is the output Q. So at the moment both A and B are low, but I'll just prove that by connecting them to a low place. So A and B low, the output Q is high. Let's make A low and B high. So you can hear the switching over there. So A is low, B is high, and the output Q is low. Swap them round. And there we go. And again, the relays click over. So we've now got 1, 0, and the output is 0. And finally, let's make both A and B high. So there we go, A and B are high, and the output Q is low. So that's the NOR gate built out of 2 electromechanical relays. So let's have a look at the last of our gates now, and it's going to be the exclusive OR. Now if you remember, with the OR gate, the output was high if A or B, which meant both of them could be high, the output would be high. Whereas the exclusive OR, the output is high when A or B are exclusively high. So if A and B are high, then the output must remain low. Now I have had to do some really quite weird wiring for this. And see if you can follow it. I've taken the output of this relay and swapped top to bottom here and fed backwards into this one, and this is going to be our output. Now I haven't got an LED on there, so I'm using this LED. I'm not using this third relay at all. I'm just using this LED here as the indication of the output. So let's switch on and see what happens. So let's start off with A and B low. So they're currently low and the output Q is low. Then let's have A low and B high. There you go, you hear the clicking and Q goes high. Swap them round and we hope to get the same thing. So there we go, that's with A high and B low. And finally, this is the important one, with both of them high, the output Q should be low. So that's an exclusive OR gate built with 2 relays. So just before we end, I thought I'd show you a really interesting use of the relays we've got on this board. And we're going to use all 3 of them. We're going to build an SR flip-flop or SR latch set reset latch. And it's a really interesting device because what it does is it stores 1 bit of data, either a 1 or a 0. So we've got 3 relays wired up. This is going to be the set relay, which sets what value of data we want to store, a 1 or a 0. And this is going to reset the system, and this relay here is going to show us the output, in other words the data that we are storing. In other words, this behaves like the sort of memory relay. So the 2 outputs here, it's Q that we're going to be looking at. Q bar is just the inverse of it. So at the moment we've got a 0 on this output relay, so we're going to take the set relay and feed in a positive pulse. So I'm going to clip that in there. Now, I hope you can see what's happened. Because this is now all energized, okay, this switch has gone up there and put a positive voltage on there, so that all of this is now positive. And so this switch has gone up and switched off Q bar and switched on Q. But can you see what happens if I now disconnect the positive from here? Well, remember that this switch is up here, and therefore all of this wire is positive, so it will stay holding the top of this positive. So if I disconnect this set line and take it out, Q remains high. In other words, it acts like some memory. But what if we want to store a 0 or reset the system? Well, because we've got a current path through this relay down to ground here, what if we put a positive pulse on this relay, the reset relay, and pull that switch up? We're going to disconnect this here, that switch is going to drop down, that's going to go to 0, and this is going to switch off. So here's the reset line. Remember, we need to make the reset line positive or high, so there we go. So we've energized this relay, disconnected all the others, and now we've gone back to the 0 state. So the really interesting thing with this setup is that if I disconnect the reset, we look at what state it's in, and we can set either a 0 or a 1, and then when we disconnect both inputs, it holds the data that we had before. So it's a very simple 1-bit memory module, but built with electromechanical relays. I thought it was worth just emphasizing that, of course, this is a 1-bit memory module. It can store a 1 or a 0. So when they built electromechanical computers, can you imagine just how many of these you would have needed if you were going to use this as your memory storage device? You would have needed thousands and thousands and thousands of them. So your computer would not only use a huge amount of power, but would, of course, fill huge rooms as well. So I do hope you enjoyed that video and you feel really confident now on how logic gates work, and the fact that you could, if you want to, it would be much bigger than this room I'm sitting in at the moment and you'd need thousands and thousands of them, but you could build a computer with regular electromechanical relays, and of course it has been done. Anyway, I'll be making another video soon and I do look forward to seeing you then.